Okay, welcome to lecture 7. We're going to discuss refraction at a spherical surface. So, remember the sign convention that when light goes from left to right, that is positive, and that's what we're going to use. So let's look at a spherical surface. So if I have something concave like that, then I can draw this axis, and roughly this would be the center of curvature. So we're going to call it C. And suppose we have the object somewhere here, right? Let me call that O. Then to see how the image from this object would appear if you are viewing from somewhere outside the lens or the outside the spherical surface. So if I have an object at O, you would have one ray that is just going straight through, right? That's a refracted ray. It goes straight through the vertex here. And then another ray, say, that is going out from the object this way. Okay, it's going out this way. So our normal would go from there through this, through the center of curvature. That's the normal, right? So this angle would be theta 1, and the ray would refract, say, to another angle theta 2. So this would be theta 2, right? So outside, when you're looking from outside here, you're seeing one ray coming out here this way and another ray that is coming out this way, right? So it would appear as if there is an image at the point of intersection, but that's right here. So it would appear as if there is an image right there, right? So now let's try to figure out uh, a relationship between the object and the image distance and the radius of curvature, like we had done previously in the case of reflection. So our radius of curvature would be this, right? This is the radius of curvature r, and then the object distance would be from O to V. That's the object distance, which we will call S, and the image distance is what we will call S prime. And so then let's look at the angles once more. So this is the theta 1 is the incident angle and the refracted angle is theta 2. So if I were to extend this line, right, this angle would also be theta 2, because this dotted line in black color, right, in this line is the same as the refracting ray. So that angle, this angle would be theta 2, right? That's theta 2. And this angle between the normal and this ray, is theta 1, right? So now if I were to write from based on the law of refraction, if I were to write that, I would have n1, right? That is the index on this side of the medium, n1, and the index on this side is n2. So n1 sine theta 1, theta 1 is the angle at which the ray going out from the object is incident on the spherical surface, is equal to n2 sine theta 2, right? Now let's look at the external angles here and here, right? Let's call this external angle next to I as alpha prime, and this angle next to O as alpha. Okay. So if I call this as point P, now if you look at the triangle CPO, CPO, O is where the object is located. A ray going up from O is incident at point P, and C is the center of curvature. So the triangle that you're looking at is this CPO. Okay, and the angle that is external to O is what we called as alpha, and this angle here between CP and PO, right? PO is the line along which the ray is incident on the spherical surface, so that angle is theta 1, right? And if we call this angle as phi, that is the angle between CP and CO as phi, the external angle is alpha, these two internal angles are phi and theta 1, so then I can write alpha as theta 1 plus phi. And similarly, if I consider the triangle CPI, then that is this CPI, right? This is along this axis, same as this refracted ray. So this angle, you know, is theta 2, right? And this external angle is what we called as alpha prime, and this angle is phi. This angle is phi. So then from triangle CPI, the external angle is alpha prime, and the internal angles is phi and theta 2. So I would have theta 2 plus phi. If you do not recall why external angle is equal to the internal angles as the sum of the opposite internal angles, I suggest you go through that. Triangle would have 180 degrees, right? And any line, any external angle would be 180 minus the internal angle. So if you do the math there, you will see that the external angle is equal to the sum of two internal angles, right? That's how we are getting these two relationships. We are considering the external angle to CPO, right? That is here, that is the alpha, and here we are considering external angle to CPI, that is this angle, right? So now we have this, from here I can write theta 1 as alpha minus phi, and theta 2 as alpha prime minus phi, right? Let's take a look at these triangles again, because it can get, while drawing these ray diagrams, it can get a little messy. So let me draw it a little better. So here we have this refracting surface, right? And let's say that's the center of curvature, right? And we have the object here. So one ray from the object is going straight through the vertex, right? Another ray is incident at point P, that's point P. So it gets reflected from the normal. So the angle is measured with respect to the normal going through the center of curvature. So it is going to go this way, right? So this is theta 1, right? That's theta 1. And if I extend this refracted ray here, this is where my image would form, right? And this angle is theta 2, okay? And we're calling this angle as phi, and this is alpha prime, this is alpha. Okay, and of course this is theta 2 as well, right? Okay, so now we have seen that n1 sine theta 1 is equal to n2 sine theta 2, and from the external angles alpha and alpha prime, we saw that theta 1 is basically equal to alpha minus phi, right, and theta 2 is equal to alpha prime minus phi. So if I plug these in and make the approximation, small angle approximation is sine theta is almost equal to theta for small angles, which is almost equal to tan theta, because tan theta is sine by cosine, and for small angles cosine is almost 1, right? So using the small angle approximation, then I can write n1 theta 1 is equal to n2 theta 2, or I can write it as n1 alpha minus phi is equal to n2 alpha prime minus phi, right? So now I am going to make the approximation that each angle alpha is tan alpha and phi is tan phi, because for the small angle approximation I have theta almost equal to tan theta, right? So now what we will do is we'll draw a perpendicular from point P. We'll draw a perpendicular here, right? And we'll call this height h, right? And we'll call this point Q, right? So now this distance from O to this vertex V is S, that is the object distance, and the distance between I to V is S prime, and from C to V is the radius of curvature R, right? So now if I look at alpha, right, that is the opposite side is H, and what we are going to do is we are going to make a very moderate approximation that for this triangle, for alpha, the tangent, we will do it as h, the opposite side, by the entire object distance s. That's a moderate approximation because this distance qv is not really negligible. But nevertheless, we are ignoring it because we are trying to do first order optics or Gaussian optics, like we have already discussed, right? So then I would have n1 alpha would be h over s, the object distance, and phi would be negative h over radius of curvature, right? And similarly here n2 for alpha prime would be h over image distance s prime minus h over r, right? So now if you reshuffle this equation, we are going to get, so we had n1 h over s minus h over r is equal to n2 divided by h over s prime minus h over r. So if I reshuffle this, I would get n1 by s minus n2 by s prime is equal to n1 minus n2 by r. But we haven't really taken the sign into consideration, our sign convention into consideration for this equation. So recall that in our sign convention, if the image is virtual, it becomes negative, right? If the image is virtual, then the distance, we take it as negative. In this case, the image is virtual because the rays coming out of the of the surface are actually not converging in reality. They're converging, it's a virtual convergence. They appear as if they are coming from this point I. So this image is a virtual image, right? So then we have to change this sign because it's a virtual image. So we're going to make it plus. And then if I look at the center of curvature is on to the left and not onto the right. So if the center of curvature is onto the left, then we consider that as negative again, right? So then I would have to put a negative sign here, or I can write this instead of n1 minus n2, I could change it to n2 minus n1 by r, right? So then we have the equation as n1 over s plus n2 over s prime is equal to n2 minus n1 by r, right? So once you have the numbers, you would need to go back to the sign convention, right? So let's look at example 2 in the textbook so that we know how to use this equation, right? So so what we have is we have a spherical surface. Again, this is example 2 in chapter 2. So we have a spherical surface, and then we have an extended object and not a point object. So if you have noticed in the previous example which we did, we just looked at a point object, but here I'm talking about an extended object, right? Then again, you still have to draw only 2-3 rays to determine where the image is going to be, right? So clearly from this extended object, right? So whatever is going up here, right, gets refracted, right, and goes through something like that, right? And then we have say something going down, right? It would, so this is going horizontally and then getting refracted. So if a ray goes in at that angle, like the refracted angle, then it would go horizontally in, right? So you would have these two rays intersect here. So now your image would form like this. So you would see an inverted image, right? And the image here is not virtual, it is real, because the rays are intersecting in reality, or not extending them back in dotted lines and not perceiving them as if they're originating from a common point, but here the rays getting refracted, the rays that are incident on the spherical surface at different angles get refracted and meet in reality, so you see a real image. Now if in the problem we have the refractive index here to be 1, right? So say something like 8, and this is, say, n2 is 1.33, something like water or glass, and the radius of curvature here is given to be 5 centimeters, right? And we have the object is at a distance of 30 centimeters, and what we have to do is first find the image distance, right? So we need to find the image distance. So again, we use our formula. Our formula is n1 by s1, or s, plus n2 by s prime is equal to n2 minus n1 by r, correct? So here n1 is 1, so we have 1, divided by s is 30. Why? Because the object is to the left of the lens or the spherical surface, and because it is to the left, the distance is positive. And here the image is inverted, but it is a real image, so we don't need to change the sign anymore. It's a real image, so it is positive. N2 is 1.33 divided by 5, sorry, divided by S prime. We have to figure out what this S prime is equal to N2 minus N1, that is 1.33 minus 1, so we would have 0.33 here, divided by the radius of curvature. What would be the sign of radius of curvature? Where is the center? The center is to the right, and if center is to the right, it is positive because light is going from left to right, right? So if the center of curvature is to the right, it is positive. If the center of curvature is to the left, then it is negative. Remember that. So because center of curvature is to the right, it is positive. We don't need to change the sign. So I have here 5 centimeters, right? So the equation is simple to solve, and once you solve, you will figure out that S prime is around 40 centimeters, right? So it comes out positive, right? So you're right, because this is a real image, so that way you can cross check, right? So then we can also figure out what is the magnification of this, right? So to figure out the magnification, what you have to do is we have to figure out how tall this is compared to how tall this is, the object and the height of the object um, and the height of the image. So let's say the height of the object is h0 or ho, and the height of the image is hi, right? We know that this angle is, if I have another ray that is say going like this, which hits the vertex, right, and then that goes like that to meet the image, and so this angle would be theta 1 and this angle would be theta 2, right? So then if I want to look at the heights, then I can write the refraction law here again, that is n1 sine theta 1, which I approximate as theta 1, is equal to n2 sine theta 2, which I approximate as theta 2, right? And thetas I can approximate as the tangent. So if I take this triangle, right, then that's theta 1. So tan theta 1 there would be h0 divided by the object distance h, right? So you would have n1 h0 by s is equal to n2, right? In case of theta 2, right, if I take this triangle, in case of theta 1 we have taken this triangle, so I have, so that's theta 1, so I have n1 h0 over s. In case of theta 2, I am going to, oh sorry, in case of theta 2, the triangle I'm going to consider is this, right? And this distance is the image distance S prime from 0 to the image point I, and this is the height of the image. So then I would have n2 hi over S prime, right? And so I need my magnification. The lateral magnification is the height of the image compared to the height of the object, right? And so I can make this hi by h0. If I take h0 there and bring the other terms here, then I would have the magnification as hi over h0, which is equal to n1 s prime by n2 s. Here we are going to put a net negative sign because another part of the sign convention is to introduce a negative sign whenever the image is inverted, right? Because if the image is inverted, this height of the image, you're measuring it below the axis, right? And below the axis would be negative. H0 is above the axis, the object is erect above the axis, so you're going from the zero origin to the top of the arrow, so that would be positive. Whereas if the image is inverted, its height would be measured in negative direction, so we are putting in a negative sign to indicate that it is inverted. So in our example, we had S, the object distance, as 30 centimeters, and using our length equation, which is n1 by s plus n2 by s prime is equal to n2 minus n1 by r, we figured out that the image distance is plus 40 centimeters. That is, we have a real image, but it is an inverted image. So the magnification, the fact that it is an inverted image, can be seen from magnification, would be negative. N1 in our case is 1 times 40 divided by N2 is 1.33 times 30, right? So that would give you, if you do the math, right, you would see that basically this gives you -1, which you could see from the ray diagrams that this height of image of height of the object was roughly proportional to the height of the image, right? Okay, so we'll stop here, and in the next lecture we'll do thick lenses and thin lenses. Thank you.